Welcome. I'm going to talk about shapes of electron orbitals. So those are S, P, D, and F. They are part of the quantum mechanical model of the atom, and the shapes have been calculated by solving sophisticated mathematical equations. The quantum mechanical model itself is a refinement of the Bohr model, so let's have a look at that again. The Bohr model proposes that electrons orbit the nucleus the way planets orbit a star. Based on the current understanding, this is not the case. Although flawed, the Bohr model is useful because it helps visualize what happens on an atomic scale, and parts of the model still hold true. The model calculated the energy levels, or shells, where the electrons might be, and it correctly solved for the number of electrons that may occupy each level. So the first energy level can hold 2 electrons. Let me draw this in. 2 electrons. The second can have up to 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And the third level as many as 18. So I'll just pop those in here. The model also correctly stated that the electrons cannot be in between the energy levels. So they have to be on an energy level. They cannot be somewhere here or here. The solutions to those quantum mechanical equations that I mentioned earlier gave probabilities for finding an electron in a particular volume of space. The shape of the orbital encompasses the volume where the chance of finding an electron is 90%. So let's have a look at those shapes. So here's an axis grid. Now let's look at the s orbital. So the s orbital is a sphere. The angular momentum number, L, is equal to 0. The magnetic number ml can have a range from minus L to plus L. Because L is 0, the only value possible is 0 as well. So there is one possible value for one s orbital. Let's have a look at the next one. So the next ones are p orbitals, and they are in the shape of a dumbbell. The angular momentum number L for all of them is 1. The magnetic number ml can again range from minus L to plus L. In this case, that means that the possible values are minus 1, 0, and plus 1. So there are 3 possible values for 3 p orbitals. The orbitals also have designations depending on the axis they are on. So for example, this one is on the z-axis, so it is pz orbital. This one is on the x-axis, so it is a px orbital, and this one is on the y-axis, so it is a py orbital. Let's move on. So the next one, the next orbitals are the d orbitals. The d orbitals are mostly clover-shaped. The angular momentum number L for all of them equals 2, or is equal to 2. The magnetic number ml can range from minus L to plus L. So in this case, that means minus 2, minus 1, 0, plus 1, and plus 2. So there are 5 possible values for 5d orbitals. These orbitals also have designations depending on the plane they are on. So this one would be d orbital xy, the next one is xz, the next one is yz, and then it gets a little bit more complicated, x squared minus y squared, and the final one, which is not exactly clover-shaped, is z squared. Let's move on. The next ones are the f orbitals. So here are some x's. Now they get a little bit more complex. So the f orbitals have complex shapes. I have drawn the first 3 because that is the limit of my drawing skills, and I suggest that you look up the others. Still, the magnetic number, so we can still do the other things. So the L value, the angular the angular momentum number L is equal to 3, which means that the ML values can range from minus L to plus L. In this case, that means minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So we have 7 possible ML values for 7 f orbitals. Now I will not go into their designations because they get more complex, just like their shapes. And also I would like to mention that there are orbitals beyond f. However, they very rarely come into play, so I will not worry about them. That is all for now, and have a good day.